In this video, we're going to go over this problem where we're asked to consider a solution prepared by mixing 0.5 moles of ammonium and 0.57 moles of ammonia in 1 liter of water. And we're told the Kb of ammonia is 1.85 times 10 to the negative fifth. And we can see here there's parts A through E of this. And so we can start off with part A. We're asked to find the pKa of the ammonium ion. And to do this, we're going to have to remember a few different equations here. We can look them up. So we can recall that Kw is equal to Ka times Kb. We're told the Kb and Kw is a constant, so we can see that Ka is going to be equal to our Kw over Kb, and Kw is 1.0 times 10 to the negative 14th. Kb is given as 1.85 times 10 to the negative fifth. So we can first solve for the Ka. So let's see what that looks like. Oops, let's see if I can't get that to come up. Here's my calculator. So we're going to do this division. And so we see we get 5.41 times 10 to the negative 10th for our Ka. And so then the pKa is just going to be equal to the negative log of the Ka. And so our pKa is going to equal negative log of our 5.41 times 10 to the negative 10th. And pKa is equal to, plug that into our calculator, negative log of 5.41 times 10 to the negative 10th. And we can see from the calculator, we get a pKa, of 9.27. So there's part A. In part B, we're asked to find our pH of this solution. And the key for part B, when we're asked to find the pH, is to recognize that we have a weak acid and its conjugate base both present. So this is a buffer solution. And so when we go to calculate the pH, we can actually use our Henderson-Hasselbalch equation. pH equals pKa plus the log of the concentration of conjugate base over the concentration of HA. And we can use this because we have a buffer solution. Notice we just found the pKa in part A, and our concentrations of conjugate base, we can say concentration of ammonia is going to be, because we're in 1 liter of solution, our concentration of ammonia is going to be 0.57 moles divided by 1, or it's going to be 0.57 molar, and the concentration of NH4 plus is going to be 0.50 molar. So we can go ahead and plug it into our equation now and say the pH is equal to 9.27 plus the log of 0.57 divided by 0.50. And again, we can plug that into our calculator. If I can't get that to come up. So we have 9.27 plus the log of 0.57 divided by 0.5, close our parentheses, and we see we get a pH equals 9.33. So there's our pH. part 2. Now, come up to part C, and we're told, predict what will happen to the pH if a small amount of base is added. What will the base react with, and how will this affect the equilibrium of the solution? So for part C, we're asked to explain. I'm going to start off by writing our equation of our buffer. Recall that when we think about a buffer, we're always going to write it from the perspective of the weak acid. So weak acid plus water in equilibrium with weak conjugate base plus hydronium. Okay, and so if we can come back up to the question, and the question is asking if a small amount of base is added. So if we add OH minus, we're adding that to this whole system. So the question is, what will the hydroxide react with? And so the hydroxide is going to react with the acid, and the acid is going to react with is the ammonium. So think about what's going to happen. If we react the hydroxide with ammonium, then some of this ammonium is going to be converted to ammonia. And so what we're doing is we are decreasing the amount of ammonium, and we are increasing the amount of ammonia. So go back to the Chatelier's principle. If we decrease the amount of our reactant and we increase the amount of our product, what that's going to do to our equilibrium, it's going to shift it back to the left. And in doing so, it's going to decrease the concentration of hydronium. And if we have a lower concentration of hydronium, the pH will increase. So we can say if we add hydroxide, it will react with NH4 and shift the equilibrium to the reactants, which will lower the concentration of hydronium. If we lower that concentration, this will raise the pH. So there's a lot going on in that sentence. So you might want to stop and work that out and make sure you understand all that's going on there. So in part D, now that we've predicted, we're actually going to go through and do this calculation. And so we have the same buffer system. We're going to add 2 milliliters of 3 molar sodium hydroxide. So let's go ahead and see how that's going to look like. I'm just going to copy that down for part D. We're adding 2.00 milliliters of 3.0 molar NaOH. And the first thing I'm going to do with that is calculate moles. So let's figure out how many moles of sodium hydroxide we have. And to get that, we're going to take out our calculator again, and we're going to say, we're going to take our 2 milliliters, or 0.002 liters, times our 3 moles per liter. And so this, we're going to see this is really adding 0.006 moles. So now we can write our balanced equation. And so we're adding our NaOH plus, and what does it react with? It reacts with our ammonium, NH4. One-way reaction arrow, because it's a strong base. So we're going to get our ammonia, aqueous, and now we just have our water as our other product. What we're now going to do is we're going to use our before-after table. This is our limiting reactant problem. And we know we have 0.006 moles of sodium hydroxide. For the ammonium, we can come back up to the problem and recall for the ammonium we are told we had 0.5 moles of ammonium and 0.57 moles of ammonia. So 0.50 and 0.57. After the reaction, all of the sodium hydroxide is gone. and we're going to lose 0.006 moles of ammonium. So we can go ahead and do that math. 0.5 minus 0.006. Oops. And I had a, there we go, calculator error. 0.5 minus 0.006, 0.494. And then we're going to add 0.006 to the other side. And so we're going to get 0.576. Once we now know the number of moles, we can come back to our Henderson-Hasselbalch equation. We might want to calculate concentrations first if it's easier. So the concentration of NH4 plus is going to be our moles, 0.494, divided by now our total volume. We are in 1 liter solution. We added 2 milliliters, so we have 1.002. So 0.494 divided by 1.002. And we get 0.493 molar. And the concentration of ammonia is going to be 0.576 divided by 1.002. 0.576 divided by 1.002 equals 0.575 molar. So finally, we can come back to our Henderson-Hasselbalch pH equals pKa plus the log of A minus over HA. And so we can plug in what we know. pH is equal to, pKa is the same from before, 9.27, plus the log of our concentrations. Just make sure we put the right ones on top. Conjugate base goes on top, 0.575 divided by 0.493. Plug that all in the calculator, 9.27 plus the log of 0.575 divided by 0.493 equals pH equals 9.34. And so just make sure this answer makes sense. What did we do? We added a tiny amount of base. The pH went to 9.34. What did we start with? 9.33. So it went up 0.01 pH units with a tiny bit of base, which is what we predicted would happen in part C. Hope that helps. Thank you.